Ashburn. I'm the Executive Director of the Association for Iron and Steel Technology, and it's my honor to welcome you to the AISTech 2026 and to the Brimacombe Memorial and AIME Keynote Lecture, which represents the opening session for this year's conference. We have 529 more presentations to follow this one, but this is the first, so thank you for being here. Now, before we begin, just a quick safety note. In case we do need to evacuate, you would please exit the stairs that are inside this room. They're either behind you in the corners or they're behind this curtain here. That'll take you down to street level. And although this is the opening session, we did actually kick things off yesterday in the morning with our golf outing. Any golfers here? Anybody play golf? A few? Okay, thank you. You helped the foundation raise over $20,000 yesterday, so thank you for braving the cold weather. We had our Young Professionals programming and our Women in Steel programming yesterday, so a good start to the conference. But this is the official opening. Our conference this year does include, as I mentioned, 530 technical presentations. That represents over 1,500 authors from 34 countries. And I'm also pleased to report that we have now in excess of just about 8,700 people registered, which crushed any prior record in our history. So thank you for being part of an AISTech record year. Now tomorrow at 8 a.m. we'll have our second plenary. This is the first one. It's called the President's Award Breakfast. That's going to feature Leon Topalian. He is the chair and CEO of Nucor. That'll begin at 8 a.m. That event is sold out to capacity at about 1,350 people. I hope you have a ticket for it. Then on Wednesday morning, our third consecutive plenary session, that'll start at 10 a.m., and this is the town hall. This is going to feature 5 industry executives, including Paul Lawrence. Paul's the CFO of Commercial Metals Company. Kevin Lewis is the CFO of U.S. Steel. Doug Matthews, the CEO of Orion Steel. We have Jack Sullivan, the CFO from Nucor, and Chris Westbrooks, who's the Chief Operating Officer of Metallus. It is another can't-miss event. We're going to focus on capital allocation strategies, very important to our industry, which has invested nearly $50 billion over the last 5 years in North America alone, let alone the rest of the world. I encourage all to get there early, to get a good seat. That'll begin at 10 a.m. on Wednesday. All of our plenary sessions, including this one, are streamed live. We hope that this format provides everyone with the opportunity to participate no matter where they might be located in the world. They will be available after the conference as well on our YouTube channel. And then running through Wednesday will be our Exposition. It's the largest ever in this building. It sold out actually in December with 652 companies represented. We'll have our attendee reception in the exhibit hall this evening from 5 to 6 p.m. and our big Chevy Silverado truck giveaway, that'll be Wednesday at 2:30 p.m., but you have to be present to win that big truck. All right, now before we begin, you have to have a blue badge or an orange student badge to attend any of our technical presentations this week. If you don't have the appropriate badge, please do stop down at our registration counter, which is on level 1, East Lobby. They'll help you out. Also, I ask if you could please mute your cell phones while you are in any session, and remember that the recording of our technical sessions is prohibited here at AISTech. Now, it's my distinct pleasure to introduce this morning's lecturer. The AIST Keith Brimacombe Memorial Lecture was established back in 1999 to honor Dr. Brimacombe's outstanding accomplishments in process metallurgy, his dedication to the steel industry, and his profound impact on many people who made their career in the steel industry. And over the 27 years since, the Brimacombe Lecture has welcomed the best and the brightest minds to the conference stage to share their insights with us. The extraordinary work of all Brimacombe lecturers, past and present, has shaped our modern understanding of steelmaking as a science, and their work will undoubtedly inspire innovation well into the future. Additional information regarding the legacy of the lecture was looping on the screen, including the biography for this year's recipient, Dr. Pinakin Chaubal. Dr. Chaubal is Vice President and Chief Technology Officer for ArcelorMittal. Time permitting, we'll have a Q&A session at the conclusion of the lecture, and we'll formally recognize Dr. Chaubal tomorrow morning at the President's Award breakfast. His lecture this morning is entitled From Pilot to Plant, Scaling Innovation for Industrial Impact in Steel Production. He's a compassionate leader for AIST. He's a champion for the steel industry. Please join me in welcoming the 2026 Keith Brimacombe Memorial AIME Keynote Lecturer, Dr. Pinakin Chaubal.
Good morning, and thank you all for being here early on Monday morning. I'd like to thank the Board of Directors of AIST for this absolutely incredible opportunity to be here today standing in front of you. I'm standing here on the shoulders of my colleagues at ArcelorMittal worldwide, and also on my predecessor company, Inland Steel, which is where I started my career. And also the many colleagues, some of whom who are here in the audience and many who are not here, who I've met and interacted with thanks to AIST. And this has been, and AIST has been, absolutely an incredible piece of my professional growth and career. So thank you to the AIST. Now, to begin, I'd like to draw your attention to 4 numbers. And the 4 numbers are 150, 22, 23, and 200,000. And I'm sure all of you are wondering, what is this guy talking about? So there's supposed to be a clicker here, but there it is. It's almost to the date today, 150 years ago, that in the town of Wilkes-Barre, Pennsylvania, not too far from here, that the AIME was established. The first, by the way, that building no longer exists. If you go there, you won't see that building. The first meeting, the first day of the meeting, there were 22 people. And you can see the plaque in the middle, which is somewhere at Wilkes-Barre. And it says 22 mining engineers got together to start AIME. The problem, though, was that the person who was the secretary of that meeting did not count himself. So there were actually 23. So learning, please don't forget to count yourself when you're in a meeting. Now, from its component divisions, AIME has grown into 4, as an umbrella organization for 4 societies, and serving about 200,000 people worldwide, professionals worldwide. And the role of AIME, as envisioned at the start, was 1, to ensure knowledge exchange, to ensure professional advancement, to ensure the welfare and safety of the people who work in our industry, and also very important, to advance technology. So 4 societies of AIME are the TMS, the Metallurgical Society, SME, AIST, and SPE. And just a personal note here, I started as a young student when I came to this country and joined the TMS. So TMS was a very important part of my first growth. I also interacted a lot with SME by virtue of papers that I presented there and some of the research work that I did. And then when I joined the steel industry, I joined ISS, which is now AIST. So really, I want to take this opportunity to acknowledge AIME because it's been a critical part of my professional and in some ways my personal growth also. Now, just to complete the picture, AIME is one of the 5 main societies that make up the United Engineering Foundation, and you might want to look at it up at what it is. It's very critical. Today, we are here also to honor the memory of Professor Keith Brimacombe. And very interesting, when I started to look at some of the history, Professor Brimacombe holds a unique honor of having led the 3 main metals and materials society of North America. He was the president of the Canadian Institute, the president of TMS, and the president of ISS, AIST's predecessor. And in 1997, he was also the AIME president-elect. And the citation below talks about his leadership efforts in strengthening the institute and unifying AIME member societies by introducing the concept of member direct and overarching program. So truly, a leader who's unmatched. I'd like to take a couple of minutes here and share a personal note. I started my career as a young faculty member, and the first summer that I had, I decided to spend it at what is now called the Missouri University of Science and Technology. My good friend Ron O'Malley is sitting right in front of me. I'm an alumni of that institute. So I decided to work for the summer with Professor David Robertson, and one fine summer afternoon, he invited me over to his house, and I spent that wonderful summer evening or summer afternoon in his backyard with him and Professor Keith Brimacombe. And what I'd like to do is to share with you some of the thoughts he shared with me, but also, more importantly, these are the thoughts, his isms, his principles that he ensured in many of his speeches, and also, most importantly, in the presidential address that he gave for TMS and for ISS. So 4 points. First of all, avoid black box. Understand processes using models instead of operating blindly. Eliminate the Thanksgiving effect, the holiday effect. Reduce dependence on experts through automation and standard procedure. And it said reduce, not eliminate. That's very critical for me. Fill the knowledge gap. Bring research directly into industrial practice. Execute the intelligent mold. We know that Professor Brimacombe did a lot of work on continuous casting, but the point here was use sensors to monitor and control processes in real time. And finally, focus on receptor capacity. Train workers continuously to adapt to new technology. All of these isms were valid then, they're valid now, and they will be valid in the future. And that brings me to the topic that I would like to share some thoughts on. Many of you, and perhaps all of you, are involved in some form or the other of advancing technology. And we go from concepts to industrialization. So I thought that might be an interesting topic to talk about today, because through my career too, that's been one of the main things that I've had to deal with. Now, when we start talking about from pilot to plant, the first thing that comes to mind is scale. Something has to be bigger, more tons per day. But the question is scale size? And what I'd like to do today is not to give you any formulas, not to give you any must-dos, but to share some thoughts and share some ideas and hope that this will lead to more discussion, because this is really what is key for AIME and key for what Professor Brimacombe also mentioned. And I would like to acknowledge that in putting some of these thoughts together, I did have a lot of help from many of you who are in this audience, so thank you for that. It's always good to go back to where you started, and I started in iron making. So the holy grail in the steel industry has always been to look at new ways to make iron and new ways to produce steel. So let's just look at where iron production has gone, and I picked the time frame from 1970 to current. Clearly, blast furnace pig iron production is one of the most important processes for converting iron ore into some form of metallic iron, okay, liquid iron in this particular case. And then the second technology, which is also very well established today, is gas-based DRI production. Now, if you look at the chart, you'll see that there was a big peak from 2000 to 2020, largely driven by China. We seem to have stabilized a little bit over the last few years, But given the growth that's coming up in India, I think we're going to see an increase in the world pig iron production through blast furnaces. At the same time, DRI production has continued to increase over the years. But what is interesting is that in the 70s, the blast furnaces were maybe making 7,000, 8,000 tons a day. Today, they are at 15,000 plus. So is it all about tons per day? All about geometric scaling? DRI production was somewhere in the range of 300 to 400,000 tons per day. Today, we are talking of 2.5 million tons per day units. Now, all along, there have been several efforts to displace, let me say, the blast furnace and DRI. I remember in 1988 when I started, there was a magazine called Iron Age, and the Iron Age cover was, "Are the blast furnaces on their way out?" or something to that effect. But today, we are still going on. Now, Corex and Finex, and I clubbed them together. This technology took effect, and today, there is about 14 million tons of production from these units worldwide. But that's petered out. And it's almost, and I think it's not going to be any more Corex and Finex in their current form that you will see being put together. So perhaps this technology is kind of on its way out. High smelt, and one of my colleagues here showed me a cover from 1996 which said, "High smelt is ready to run." That was 20 years ago. Today, in the last few years, we are starting to see some growth in high smelt in China. But the jury is still out there whether it will become or it will scale to the level that we expect and be able to replace the conventional iron making processes. We look at the same thing in steel making also. Open hearts are almost non-existent. But all through this, era, the last 30-odd years, you can see that the production of electric arc furnaces has been steadily increasing. The share went down a little bit at the same time as the iron making or the blast furnace technology in China was growing, but that never stopped the production of EAFs. What is interesting that I found was that even in the 70s, there were already electric arc furnaces with about heat sizes of 400 tons. And today, you're seeing more and more electric furnaces being built in the 350 to 400 ton heat sizes. So in the case of electric furnace technology, you may argue that size has not been the critical aspect of scaling, but there are certainly others. The productivity, the efficiencies have grown significantly. So it comes back to the main concept or the main thought that is it really all about size? Is scaling all about size? And maybe we need to look at some other things. So of course, when you start looking at these ideas, the first thing to do is to look and see what work has been done before. And for a topic that I believe is so important for all of us, because we are constantly at the lookout for scaling, lookout for developing new technology. There is very little work that has been reported out in our conferences. So my good friend Ian, who I see sitting right here, helped me out a little bit, and I would like to go back. I don't know what happened here. Oops. Oh. There seems to be a slide missing. I'm sorry, but, oh, okay, maybe it's my fault. But before I get to that point, I'd just like to come back to this slide here. The question of why this topic starts to become very important today. If you look on one side or your left-hand side, you'll see there is a plethora of technologies being developed for, let's call it, new iron making or alternate iron making. And what is very interesting is that many of these technology developers are not the traditional sources that we think about, not the big OEMs, not the steel producers, not the iron ore producers, but really what we call startups. Groups that are coming from backgrounds which have nothing to do with the iron and steel industry. And for the first time that I can think of, we in the steel industry are talking about startups in terms of our own manufacturing. It's a very, very exciting time and a very, very unique time. And what this does bring is it brings a certain amount of challenges. Innovation cycles are becoming faster, potential to have higher amount of risk. Those of us who have to look at integrating these technologies have to worry about, are these going to be industry reliable? How will we integrate them into existing plants? What will be the economics? Because we are not traditionally used to looking at startups as a way to integrate into our own processes. So now I think I'm back on track with the slides here. So building on the earlier work. So there is a lot of work, or not a lot of work, but there has been some focused work that's been done by several people. McNulty focused a lot on ramp-ups. What are the key factors that lead to successful ramp-ups? And interestingly, it's not all about technology. There are many other factors that were involved. Dr. Wasmund did a lot of work initially, presented at a lot of our conferences, and I tried to extract just a few, or just one key comment. Very difficult from a series of papers, right? But I hope I did the right thing here. So his main concept was learning first. Don't start to commit capital, because committing capital leads to lots of issues and pressures that you can't deal with. So commit capital after you have proof that things can work. Ian Cameron, who's here, has been doing a lot of work also lately and presented a number of papers at this conference. And I hope that as a result of the discussions we are having today, we will start to see more and more effort being placed in this area, because this is really going to be critical for us to move forward. So Ian, if I did summarize it correctly, de-risk first, and we'll come back to these concepts in a few minutes also. Invest to accelerate ramp-up. Now, at the same time, over the years, there have been many frameworks developed. I think a lot of us are familiar with the TRLs, the Technology Readiness Levels, coming from NASA. But when we started to dig in, we found that over the years, many other frameworks to address the scaling issue have been developed. Integration readiness level. Can this technology work together? Maturity levels. Can we build it at scale? Commercial readiness levels. Can it be sold? Can it be financed and scaled? EU has developed its own framework for can it be sustainable? How to integrate industrial deployment specifically for EU sectors? And lately, adoption readiness level. What prevents adoption? And very interesting, this year at Davos, this topic was one of the forefronts. They looked at it both from the standpoint of course, scaling for AI, and which is very, very glamorous, but also scaling for heavy industries and for the energy transition. So when you look at this, what you see is technology readiness is only one part of scaling. And probably becoming, well, it is important, but all the others are also very, very critical. So the question is now, how do we take all these concepts? How do we take all of this into thinking about scaling at a fast pace, scaling with success? So scaling is really all about risk management and risk associated with uncertainty. The problem is that uncertainty is not only difficult to predict, but there is a lot of hidden uncertainty. And unless we change our way of thinking to start looking for what is the hidden potential uncertainty, we will run into roadblocks that are going to be difficult to solve. At early stages of development, so this is pre-pilot stage, the scientific principles are investigated. This is critical. But once you're in the pilot stage, at least it's working. Something is being produced. A lot of the basic science has been already looked at. And really for successful industrialization, It's what we call system-level risk mitigation, system-level risk understanding, which becomes critical. So I'd like to suggest that we talk about scale-up and reframe the wording to say it's about anticipating and managing the emergence of risk. And you can see that this wording or this reframing is quite consistent with some of the earlier slides where I spoke about the different frameworks and spoke about the different work that's been done previously. The second part, which also is critical in our thought process, is that a lot of focus is given from the pilot to the first of a kind. There is significant attention from senior management. You put your best people from all areas on this. But really, when we talk about industrialization, it's not just the first of a kind. It's the second, the third, the fourth, the fifth, the nth of a kind. At every stage there is learning. And every stage we have found that it is possible to have failures that can completely derail the growth of the technology. So, while there is a nice word, the valley of death, that's given from the pilot to the first of a kind, there was really no mention of what happens after that. So we decided, okay, let's give it a word. So we call it the missing middle. And you'll see that a lot of what I talk about in the next half hour or so will be addressing more of the missing middle. So how did we go about trying to understand a little more of what has been the success and failure of industrial scaling? Followed the time-honored case study methodology, looking at three things. First, to evaluate cases. What happened and why? Second, to extract from there the key learnings. What did we learn about operational, technical, governance, not just the technical part, but all the other things that are important in terms of ensuring that we are successful? And then derive from this analysis, what are the relevant learnings that we need to take forward in our next generation development? We looked at it through three lenses. The UDO framework, and I'm sure you're wondering what is UDO. I'll talk about that in a minute. The multi-layer scaling, and how to close the learning scale gap. So what is UDO? But first of all, a disclaimer. This is not words that I or my colleagues developed. It came from a study that was done for social innovation in Canada. I don't know, Ian, everything seems to be coming from Canada. And then we adopted it for our industry, for what we are looking at. And what does UDO stand for? So first of all, scale up. Industrial viability. Does it work industrially? Scale deep. Adoption. Does or do organizations learn to run the technology reliably? And scale out, replication. Can it be replicated across sites, across generations, across geographies? In fact, in order to be successful, we are not just after one of these, not just after scale up or not just after scale deep, but for all of this. All these need to be successful for us to truly consider that we have, in fact, industrialized successfully. And you will notice that because the scale out part is there, there is never an end point to the development of technology. And that's where we come back and say, okay, the nth of a kind, or going from the first of a kind to the nth of a kind is also very critical, because at each stage you're learning something, and you have to remove risks as you go forward. What's the multi-layer scaling process? In order to be successful, it's not just one group in an organization that is critical. The successful development of technology comes from many different groups working together. Research, engineering, operations, business, and all these groups interact with each other to different levels at different stages of technology development. But rather than look at it as serial and say that one group comes in and goes out, real success will come when all groups are working together from conception to finalization. And that's why in this picture here, we show that industrialization happens here. It's really all about ensuring all the layers are there all the time, even if their interaction or involvement may be different at different stages. And the third part, or the third lens, was how are we using learning to close the scaling gap? Are we focusing on the right things at each of the stages to ensure that the gaps are closed? Or are we just taking the easy way out and kicking the can down the road? So just to give you a rough idea, we looked at many different technologies. And in the case of steel making, just to put a few of them in front of you, because here you have technologies which are at different scales. Some are greenfield, some are brownfield, some are mixtures of greenfield and brownfield. Some you would consider successful and continuing the development, and some perhaps have probably petered out and you won't see any further development. So CSP-based technology, or thin slab casting direct rolling, is pretty much becoming the new standard. It's a brownfield, greenfield concept. Cast strip, there are 2 units, but I don't think we'll see any more. Mulpic is a brownfield technology integrated for cooling for heavy plates, intensive cooling. A hybrid filter is one that came from the coal industry or the cement industry, and it was adapted to improve the efficiencies and reduce the capital costs for dust mitigation. Jet vapor deposition, and I think there was some discussion on that last year, is a technology that's been there for directly coating steel at roughly 100 degrees centigrade or thereabouts. It's been developed for 10 years. It's successful, but the second of a kind is still not out there. The iron carbide process, I think some of us may remember that one, where a couple of plants were built, but we couldn't take it beyond that. So we looked at many cases, small, large, brownfield, greenfield, just to give us an idea of what are the success and failure factors. And to have a little bit of fun, but more than that, to ensure that we are also doing benchmarking and learning from other manufacturing industries, we looked at a number of cases of large-scale development in other industries. So just to give you a feel for how far we looked at the aerospace industry. And you may argue, is the space shuttle a success or a failure? Or is the Starship concept going to be the next success? We looked at the petrochemical industry, and we look at that quite a bit. We looked at the mineral processing and the iron ore industry. And we looked at concepts which sometimes have to be developed for one particular application, but the next of a kind is not going to be there. So putting all that together, I'll summarize some of the key points that came out. And it's very interesting because this was a common theme across all. First of all, projects do not fail because they do not work. Something is being produced. But really, what we found was that when you start to industrialize, when industrial reality comes in, it exposes risks, and risks that were often not learned before or not anticipated before. And the second thing, the second point that was very clearly coming out, was that scale does not solve problems. Don't kick the can down the road. It actually exposes them. And sometimes the exposure can be very, very painful to deal with. So some key learnings. And these are key learnings in relation to what we should be avoiding or what we should be aware of and make sure that we are addressing it. First of all, safety. I mean, this is very, very critical for us. It always has been, but it's even far more critical. Safety has to be embedded in every phase of development. Why is it critical? Because very often what we found was that safety issues that were being looked at the smaller scales were localized issues. But once you started to integrate, once scale developed, once integration across the system occurred, the safety aspects affected the entire system and became far more difficult to deal with. So safety has to be integrated in every aspect or every part of development. Do not expect that because the pilot has been a success, it means that you're ready for industrialization and widespread rollout. I've talked about risks, and the process of scaling is a process of developing the right learning to be able to eliminate the risks. Very often what we found is over-exuberance has led to capital being invested much before we were ready to say that we have learned enough from that particular stage. And we need to make sure that we manage this expectation properly. Very often, we also found that the scale or the level at which the project is being run, the focus was on ensuring the performance for that particular application. But at the end of the day, we are talking about scaling out, we are talking about rolling out solutions, we are talking about broad applications, and we need to ensure that robustness at each stage is understood, because that's going to be critical to scale out faster. And finally, system is underestimated. Again, probably over-exuberance of the teams that are there. So what do I mean by systems? There are many aspects of systems. Technical scalability, material durability. I think this is very, very critical. What we see works at smaller scales in terms of the durability of materials may not work at larger scales. And just a couple of days ago, I was reading an article talking about undersea pipelines, where the joints between the different sections are made with what's called GINA gaskets. And those testing was done with the corrosion conditions that were expected, but not under the mechanical stresses that were expected. So these pipelines are supposed to last for 100 years, but now the engineers are starting to think maybe 50 to 75. So a major flaw in material durability. So not to forget material durability. Financial bankability, meaning that at every stage we need to make sure that the deliverables of that stage in terms of the financial aspects are well understood and well respected. Because it's very easy to have fall downs, and if financial backing is not there, then there's going to be no further development. Ecosystem readiness. This means your supply chain, whether it's for the raw materials, whether it's for spare parts, this also needs to be understood at very early stages. If we try to kick that down the road, kick that can down the road, we will run into problems again. Because in the design and the development phase, you need to understand what is it that is going to be there to support you as the technology develops. And finally, human workforce. This is sometimes a neglected aspect. When you're first starting up, you're putting your best people, you're putting all the right resources there. Probably you're over in terms of the number of resources that you need. But that's required at the first stages. But as technology progresses, as you start to roll out, the level of people who need to be trained, the number of people who need to operate is going to be changing. And you need to ensure that your workforce is well trained and is capable. And included in here is the fact that you have to have the right champion. That's very critical. So what did we also learn in terms of accelerating industrialization? Because again, as I mentioned before, one of the key tasks for us is to be able to develop these technologies faster. The scale or the timing that we had before is not going to be acceptable moving out in the future. Technology is changing very fast. Customer expectations are changing very fast. Environmental and regulations are changing very fast. And we have to be adaptable. So a couple of things came out of our studies. First of all, key is learning velocity. And learning velocity is basically learning how to manage risks. Don't rush the schedules. If you are managing your risks properly, if you're understanding the gaps, if you're developing the right learnings, the schedule will automatically compress. Modular design. It's important to think about modular design because modular design allows you to optimize small parts and to ensure that these can be rolled out very quickly. There was an example, and I believe it was on the high-pressure acid leaching. It was a technology developed for nickel laterites. And it was largely developed by engineering companies in the Western, what we can call the Western world. And after a couple of developments, it seemed to have stymied. The technology development was taken over in China. They looked at modularization, a little bit of a mouthful here. And they looked at how to, of course, develop these models more cheaply. CapEx came down. Reliability significantly improved. Startup really became easier. And as a result of that, the HPAL technology took off. So again, modularization is very important. Demo plants. We normally look at demo plants as a way to prove what we think should be proven, what we want to prove. But really, demo plants should be looked at as platforms which are going to have system learning, system integration learning included in them. So therefore, try to have demo plants which will allow us to expose risks that we have not expected, expose risks that will come at the next stages. Bankable scale path. Clearly, financial backing is required at every stage of development, and that ecosystem, that structure has to be well understood in terms of ensuring that at each stage you are producing or you are developing and giving the right results that are important for the financial backing to continue all the way through. And the last part, I think, is very, very critical, and it also goes back to some of the comments that you may hopefully recall from the comments that I mentioned about that Keith Brimacombe gave, which is to embed R&D. It's very often we find that after the initial stages, the R&D organization is taken out of the development. And because we are talking about the fact that we will always have new risks that will be exposed, there is going to be new solutions that have to be developed. And having R&D embedded into this whole process becomes very, very critical. We saw numerous cases where in the initial stages there was the R&D embedded, but in the final stages they were taken out, and the development of the process has stopped. So, what is again important is to make sure that we do not forget that the first of a kind to the nth of a kind, this journey is also very, very important. It's at this replication stage that viability in terms of reliability, viability in terms of operational efficiency, viability in terms of cost control, viability in terms of capex reduction comes. And these stages become as important, probably more important than the initial stages of pilot to the first of a kind in terms of ensuring that viability and sustainability of the technology is there. So I'd just like to take a couple of minutes to look forward a little bit. Scaling innovation in steel making is our bread and butter. It's part of our industry, and we have to continually innovate, right? So what are the key drivers? What are the key drivers that are going to become more and more critical moving forward? Safety, sustainability, and license to operate. And the rules and regulations for each of these is changing very, very fast. When we start to look not only at the Americas and the Europe, but we also start to look at the Eastern world, you will see that these factors, these parameters are becoming more and more critical. And what is going to drive us is to ensure that we continue to be at the top level and even anticipating potentially what these changes will be. Complexity demands capital discipline. Our processes are going to become more and more complex. That is a given. We have to not only include the sustainability part of it, but we also have to include the fact that we have to be far more efficient. We have to include the fact that our customers are demanding far more complex solutions on time, at the right quality, and probably even in advance of their own expectations. Therefore, the complexity of our development is going to increase. And this will demand that we have good capital discipline. Because very often, and I hate to say this, but the financial world is not as patient as some of us engineers are. But we have to look at marrying this. Workforce transformation. This is absolutely amazing to see how workforce is transforming almost by the year. Every year, the expectations of the engineers who are coming into our organization is changing. The tools that they're looking at is changing. And we have to make sure that we ensure that in our development, we make sure that the workforce that we have been are looking at are able to be adapted, are able to be trained to the developments that we are going to be bringing forth. Now, given all these drivers, one of the biggest risks that I see is the fact that our developments may fall into this aspect of being rigid. We have to be able to adapt. If we are scaling without thinking of adaptability, whether it's adaptability to the parameters on the left-hand side, or adaptability to changing situations with the supply chain, with the geopolitical situations, we will run the risk of failure. So right in terms of our developments, right in terms of our scaling up, we need to make sure that we ensure that we are not making our developments rigid, that they are becoming adaptable. Tools, skills, and mindset for future scale-up. I think this is very critical. The tools that we had 15, 20 years ago were just in their infancy. Tools and skills, or tools and skills and also mindset for the future are changing. I just mentioned the fact that the workforce that's coming in is a completely different mindset from those that were coming in 20, 30, 40 years ago. So we have to be able to adapt. So what are some of the areas that we need to look at very carefully in moving forward? AI and digitalization. There is no doubt that we need to embed AI and digitalization in everything that we do. But what I'd like to point out is that perhaps what is also very critical is that we look at using these technologies as a way to help us analyze risks, as a way to help us maybe even predict risks. Now that may be a little provocative statement here, but we are doing a lot of work in our industry at using these technologies for predictive maintenance, for predicting quality. So why not also look at ways on how we can use these technologies to unearth risks that are latent, unearth uncertainties that are latent, because that will certainly go a long way in helping us solve the problems. Demonstration platforms. When we look at different phases, we need to make sure that we are looking at developing these platforms in a way to allow us to reveal what system-level risks can come up. Not just solve or not just prove the point that we think we should prove, but also to be able to find out potentially what may derail us in the future. Integration engineering, very important. We need to coordinate across processes, across the utility chain, across the digital systems that are existing in the plants, the supply chain. All of this has to be brought into our thinking and integrated in every aspect of our technology development. Data-driven learning. And again, if you think back, this is one of the key points that Professor Brimacombe always made. Using real-time operational feedback to ensure that we are in developing the so-called digital twins, which are very, very critical not only in terms of optimizing, not only in terms of ensuring that each stage is working properly, but also as a way to ensure that the next stages can be worked properly. Also as a way to ensure that we are able to train our workforce in an appropriate way. Strong governance. What do I mean by strong governance? I think it's very critical to always have a third eye. We are very often, in terms of our developments, closed. But what I've seen very often happen, that when you bring in a third party or a fourth party or a fifth party to look, different things get revealed. And I would strongly urge that moving forward, this is going to be a critical aspect and a very important part of a successful technology development. Cross-functional teams. We mentioned that before. Absolutely important to ensure that at every stage of the development, we have cross-functional teams. All those teams that are important for the development should be there from the very beginning. Integrate all of them. That's really very, very critical. An uncertainty mindset. Now, this might sound a little bit negative because you say, we always should be looking forward, looking at the positive. But looking at uncertainty as a way, as a positive aspect, I think is very critical because it helps us to understand what can go wrong. This kind of a mindset needs to be inculcated in the entire workforce, all the people who are involved in the development of the technology. It may seem a little bit odd, but I hope that in some of the comments and some of the thoughts that I expressed, it was clear that eliminating uncertainty, ensuring transparency is really a critical part of successful development of technology. Just some final words. So real measure of success, of innovation, of industrialization is not just based on invention speed, not how fast we get there, but really how fast organizations industrialize learning relative to uncertainty. Learning related to all aspects of what makes the process successful. Scaling up, scaling deep, and scaling out. Because scaling, in my mind, is not just a single milestone. It is really an organizational evolution. And we need to keep that in mind. I tried to summarize all of what we learned in about 4 boxes. Technologies that we develop have to be adaptable. Methodical replication, going back to the concept of modularization, going back to the concept that each module needs to be working perfectly, not to have too many new things at the same time. Build and replicate with confidence, build and replicate once robustness of different modules are established. Disciplined intelligence. Disciplined intelligence here refers to the point that we need to ensure that at each stage we are ensuring that the dominant uncertainties are being removed, are being retired before we move on. And that requires a level of self-introspection also, a level of transparency also, to ensure that we are not only discussing what are the pros and cons or the issues that we are facing, but also looking at ensuring that we are developing these with the right level of what should I call robustness and the right level of confidence before we move ahead to the next steps. And finally, although I mentioned it briefly, it's absolutely critical to have very strong industrial leadership, having very strong champions. In almost all the cases that we saw, without having the right level, the right champion, at the right level in the organization, it was very, very difficult to successfully industrialize. Because very often, the teams have to be focused. Very often, the vision has to be clear. And most of this is never done by a democratic process. It requires someone having strong stance, someone standing out of the crowd and ensuring that the process continues, that the vision is maintained. And this really is a very, very critical part of the whole success. So in all of this discussion and all of these thoughts that I'm hoping that I brought out quite clearly, didn't talk too much about technology, talked more about many of the other aspects that are so critical to successful scaling, to successfully innovate. And that brings me back to where it all started. And I would like to just acknowledge again the role of AIME and the role of Professor Brimacombe in this journey of continuing evolution of technology. So thank you very much for your time, and thank you very much for learning or hearing me out patiently.
Time for a few questions?
Sure.
Thanks a lot for that really excellent, insightful presentation, and especially integrating the thoughts of Keith Brimacombe.
Brian, please tell us your name.
Oh, I'm Brian Thomas, Colorado School of Mines. I'm interested in the two continuous casting technologies that you compared, CSP versus cast strip. Please tell us, why is it that the thin slab casting process has become the new standard and cast strip is much slower to be adapted?
I surely would have expected a question like that from Brian.
Well,
I think it's a question, maybe just going back to some of the thoughts that I expressed. Pardon me for a minute here. Now, everyone, I'm sure, will have their own thoughts and views. But adaptability and the ability to scale out, I think, are the two key points here, right? If you look at thin slab casting and direct rolling, it has evolved to not only deal with producing a thin strip, but to develop and produce products that go across the board. Now, there is still a lot of products that still have to be developed, but we are making products out of that which are, you know, an inch thick to now even maybe less than 0.8 centimeters thick, 0.8 inches thick, right? Sorry, 0.8 millimeters thick. Thank you. So technology developed. It was also important that it was adapted to different customers. And in the case of direct casting and rolling, twin roll casting, besides a lot of other technical issues, I think the product range was far too narrow. That's my short answer, Brian. I'll come to you, John, in a minute. Yeah.
Good morning. Chen Zhao from Purdue University Northwest. Thank you for this so comprehensive and insightful lecture. You are actually one of the pioneers to utilize simulation visualization to blast furnace. You just mentioned AI and digitalization can be a very powerful tool. What's your vision? How to effectively utilize the digital twin in the AV stage to analyze risk, to de-risk and speed up, not just first of kind stage. Thank you.
Okay. Thank you, Chen. I think what is very important in the way we look at scaling up, the way we look at developing technology, is that at each stage we are looking at bringing forward data, information, and I say information now because modern tools can take any kind of information and integrate them into developing these digital twins. Very often, I think in the initial stages, it was more about trying to learn some concepts, trying to prove a particular point here and there, but not with the view of developing the digital twins. And if you take that view, that at each stage we are going to get data, we are going to get information, And we are going to integrate this into these new tools that we have available to us. That is the way to make sure that we continue to develop these digital twins. And just as when we develop CFD models and we start to understand processes better, start to look inside processes, without actually looking inside them, right? These new technologies, in combination with CFD modeling and thermodynamics and kinetics, don't forget, they're all very important, will allow us to even go further beyond and improve the way we look at the next phases of development. So I think it's all an integrated process, but we have to have that mindset that this is where we want to go, this is what we want to do, and that's very critical. Professor Spear.
Take one more.
John Spear, thank you so much for that talk. In the U.S. in particular, I think that the industry is pretty good at working together collaboratively in early stage R&D and pilot scale demonstration programs, and the government participates in that, for example, through the Department of Energy in pre-competitive stages. And then you have to cross the valley of death, right, that you talked about. And I'm wondering, is there a role for more collaboration at that stage where companies could work together on full-scale activities and consider them to be pre-competitive, and then the scale out becomes the competitive aspect, so that we learn together farther along in the process development? I don't know if that question made sense, but...
Yeah. Oh, thanks, John. I always wondered about it because it looks like the first of a kind is where the value of death, the first of a kind is where things started to stop, and largely because the financial backing was not there. Is the first of a kind a pre-competitive spot? I think that's the key issue. And I hate to say this, as consolidation has occurred in the steel industry, and now even in the Eastern world, you see a lot of consolidation occurring. Even these first of a kinds are being considered as competitive advantages. And that's making it more and more difficult for companies to come together, organizations to come together to actually move technology forward. So this is a little bit of a, let me say, a backward move for the global industry. But perhaps out of the fact that now we have big conglomerates, there will be opportunities for technologies to move forward, and you don't need all the outside support. But that's why I think it's absolutely amazing for me to see producers. Thank you.
How about a nice round of applause for So we'll be recognizing Dr. Chaubal tomorrow morning with the President's Breakfast, and this will conclude our opening session. I hope you all have a great experience at AISTech 2026. Thank you.